Hi everyone, and welcome to another episode of Mr. Carlson's Lab. Today we're going to take a look at a very neat collectible device known as an AM broadcaster. This was made by Night Kit way back when, and it essentially allowed you to be your own small radio station. For example, you could plug a record player into this device and it would transmit the music from that record player to a nearby AM radio or communications receiver. Now, this device has some pretty heavy restrictions on it. The antenna can only be so long, and it can only put out so much power so that it doesn't interfere with adjacent radio stations. So, for example, how you would tune this device is you would look for an open spot on the AM broadcast band, so a nice quiet area. You would tune this device to that area, and then it would allow you to play your music in that little chunk of space on the AM broadcast band. Now, you wouldn't want to try to play this on top of another radio station because it would heterodyne and make all sorts of funny noises and whistles and things like that, so you had to look for the quietest spot that you could find. So it is a really neat little device. What we're going to do is, if it doesn't work, we're going to make it work, and we'll try it out. We'll see how well this little AM broadcaster works. So let's get started. Here you are, sitting right next to me at the bench in the lab, so let's see what we're up against. First of all, the Night Kit radio broadcaster and amplifier came in its own box, the original box, which is kind of neat. The box itself is in pretty rough condition, but that's to be expected, just due to the age of the device. And the unit itself is in very nice condition as well. This could very easily be cleaned up. The paint shows signs of normal wear and tear, but nothing too major. I do notice, though, that the volume control knob does look like it's on a bit of an angle, so it may have taken a hit or a drop at one time. You can see that there. So let's see if it moves okay. And it does. It feels really smooth, actually, so it'll probably be just fine. On the top side of the chassis, we can see the tube numbers and what they do. So they've actually marked all this right on the top side of the chassis, which is really nice. So 50C5 is a very common All-American 5 and All-American 6 radio tube. These were used in many series sets. They're using one as an oscillator and one as a modulator. They're both the same type of vacuum tube. Whenever you see a tube number like this, 50C5, 50 is the amount of volts it takes to light that filament up. So it's a 50-volt filament. C is a factory designation letter, so C just allows you to differentiate this between other vacuum tubes. And 5 means that it has 5 useful elements inside that vacuum tube. So if we go down to a 12AX7, very common tube used in guitar amplifiers even today. 12 means what? The filament voltage. It's actually 12.6, but they didn't make it a 12.6 AX7, so it's 12AX7. They were nice to make the filaments inside this vacuum tube center tapped as well, so it's really universal, this tube. That's why they are still so common. So you can run the tube at 6.3 volt filament or a 12.6 volt filament. AX, again, is a factory designation, so factory designation letters right there, so you can just differentiate this between other tubes. And 7 means that it has 7 useful elements inside the vacuum tube. So if you're a modern day person dealing with modern electronics, a 12AX7 has 2 triodes inside. So if you want to compare a triode to an N-channel FET, you can. So this is technically 2 N-channel FETs in one glass envelope. Kind of neat. These are the inputs right here. So different types of phono inputs right here, magnetic and crystal. This is the frequency adjustment. So this is what allows the movement of this device. So you can move this device to an open portion of the AM broadcast band, to the quietest portion you can find, just by tuning this little control right here. This is an audio transformer, so this can also be used as an amplifier. So say you have a record player and you don't have an amplifier. You can plug your record player into this and use this as an amplifier as well. Just attach a speaker to these 2 terminals right here where it says speaker, and away you go. So nice little universal device. Take get you playing your records in short order. So what I'm going to do now is turn the device upside down. I'll remove these 4 screws right here, and that should get us into the bottom here. As you can see, the top side of the chassis is like this, and then the bottom side is like this. So this is going to hold the bottom portion of the chassis on. So we'll take a look inside and see what we're up against. Hopefully the person that assembled this, these are kits, so hopefully the person that assembled this didn't use a butter knife and a blowtorch like I've seen many times before. Let's open this up together. So the first thing that I want to do is remove the tubes, because I don't want to be putting the weight on these little tips right here. So these are known as the evacuation point in a vacuum tube, and the little chrome spot that you see in the vacuum tube is known as getter material, and that's where they flash that material onto the bulb. The reason that they have this kind of a chrome looking cap in them, sometimes it's on the side of the tube as well, is that's a material that they put inside the tube and they flash it onto the bulb, and that absorbs any impurities that leach out of the metals inside the tube over time. You got to remember that these things are getting really, really hot. The 50C5 gets extremely hot. It's got a really large filament in the center. You can see that white little blob at the bottom there. That's part of the filament in there. These things get like extremely hot, hot as the blazes of hell. So if you ever touch something like this, you'll really get a bad burn. You always have to be very, very careful around a tube like a 50C5. Any type of a power tube that drives a transformer, anything like that, they get really, really hot. 12AX7s get fairly warm, nothing like these tubes right here. And just over time, that comes with experience. You get to know which tubes are extremely warm. At any rate, as the tube gets hot and cold and hot and cold, the metals inside, they give off impurities. They off-gas inside the tube, and this chrome material that you see inside the tube, it looks like a chrome-looking material, almost, kind of mirror-like inside. That getter compound that's been flashed on the bulb will absorb those impurities that are let off inside this throughout the vacuum tube's life. When you start to see this material go a chocolate brown color is when the vacuum tube is, this material is getting used up. Let's put it that way. If you ever see this material and it looks white and flaky on the inside, so it's the same color as the writing here, and it's really flaky, sometimes you can tap the tube and it comes off, that means that the tube is now at atmosphere, so basically it's drawn air. So there's a crack in the bulb somewhere, or on the bottom portion of the bulb where the pins come out, right here, sometimes they crack and it's drawn air, and this whole thing will just go white, like a white flaky kind of cakey compound inside. Another question I get is it okay to handle vacuum tubes with your fingers when they're cold? Yes, it's absolutely fine. It's just standard glass. The larger power tubes are made out of Pyrex or a glass called Nonex. Bendix, the Bendix Corporation that made the tubes for pretty specific application, their tubes were, the majority of them were made out of a glass called Nonex. So, in order to get inside this unit, what I'm going to do is remove these 4 screws here, and hopefully the person that assembled this, again, these are kits, the person that assembled this didn't use a butter knife, a roll of solder, and a blowtorch. Believe me, some of the things that I've opened up look just like that, if not worse. So hopefully this has been put together by somebody that took some pride in their workmanship. Okay, the moment of truth. What do you think it's going to look like in there? Good, bad, ugly? Here we go. Let's find out. That's looking really nice, and it's also looking all original. That is very nice. Well, I do see a J-hooked component right here. Somebody may have installed this in the wrong area at one time, and then they used a J-hook to reconnect it. I'm going to locate a schematic on this, and we'll also take a look at the schematic. Looks like it has the original selenium rectifier in it, and the capacitors. I wonder if the capacitors are still good. It would be neat to be able to bring this thing up slowly on a Variac and see if the thing just actually still functions. It looks like it's been put together very well. So somebody did take pride in what they did, and that's really nice to see. Oscillator coil looks really nice. The capacitors around the oscillator coil, well, they look like standard capacitors. Standard capacitors, especially this type of ceramic capacitor around an oscillator coil in an oscillator circuit, equals drift in a bad way. So this thing could use some NP0 style capacitors in this little area right here, and that would probably really improve the performance of this little unit. So it would stop it from drifting around. So capacitors like this, just standard ceramic capacitors, they really move around in temperature. So when I say they move around, I mean their capacitance moves around with just a minute amount of temperature. If there's any movement in capacitance around this oscillator coil here, this thing is going to move around on the AM broadcast band. So the thing is, way back when, NP0 style capacitors were pricey. So now they can be had for very, very reasonable prices. I've got lots of them, so if this thing does move around, chances are I'll end up doing that. So it is looking like it's in very nice condition. So what I'm going to do is just quickly test these capacitors, look at the diode here, and if they are looking like they're okay, I'm going to bring this up very slowly on a current limited variac isolation transformer and see if this thing comes to life just the way it is. That would be really neat. And of course, if I ever wanted to use this thing down the road, I would have to replace this capacitor here, and get rid of the selenium rectifier for sure. So those are the things that would definitely need to go. The rest of the stuff, there is no wax capacitors inside this thing, so pretty much everything else, if it's intolerance, could be left alone, theoretically. Now, this also brings me to the safety of operating a device like this. And there is quite a few things that need to be known before you start to work on something like this. So first of all, there is no transformer on this chassis that isolates you from the line. This line cord goes directly into this unit. The tubes themselves, the filaments are in series, most likely with some form of a dropping resistor in there somewhere. And that means that in some way, shape, or form, the chassis of this device is somehow going to be connected to this line cord. That makes working on devices like this rather dangerous, and you really need to know what you're doing. So before you work on something like this or try to experiment with this, definitely learn about what you're working on, because this thing has line voltage inside that's been rectified by selenium rectifier, so it's changed to DC and then filtered, and these capacitors hold a very large charge, and you could get a lethal shock in something like this. So definitely know what you're doing. Myself, when I operate this thing, I'm going to be using this on an isolation transformer just because, again, one portion of the line cord is most likely going to be somehow coupled to this chassis. And as you can see, we have external inputs from something else that have to run in here. So if this thing is plugged in the wrong way or something is faulty on the bottom side of the chassis, it could make this chassis live. If this chassis is live, this is extremely dangerous. And that's why when I'm working on something like this, I always use an isolation transformer, especially with something like this, because the construction is somewhat similar to an All-American 5 or All-American 6 radio. There is no transformer to isolate you from the line. And that is a very, very dangerous thing. So whenever you see tubes that have 50 or 25, a lot of them that say 12, 35, like the 35W4, things like that, that usually means that the radio itself has a series set of vacuum tubes in it, and that means that it's one side of the line cord is connected to the chassis in some way, shape, or form. What I'm going to do is I'm going to get the schematic, and we'll take a look at the schematic, and I'll explain a little bit more about this. So if you're following along and you have one of these things, you're doing so at your own risk. Let's take a look at the schematic diagram for this night kit broadcaster and amplifier and get an idea of what the engineers were thinking of at Allied Radio or Night Kit. We'll start over here with the two 50C5 tubes. So these circles here with the dots and everything inside, these little dashes and everything, these are the vacuum tubes themselves. This is the symbol for a vacuum tube. Whenever you see half circles like this, that indicates that a tube is split in half. And as you can see, V1A and V1B. This is one triode inside that vacuum tube, and this is the other triode inside that vacuum tube. So this is the 12AX7 here. As you can see, there's two parts, one part right here and one part right here. So one part right here and one part right here. Again, if you're looking at this through modern eyes, you could look at these as N-channel FETs. So this would be the drain, the gate, and the source, if you wanted to look at it like that. So moving back over here, again, the 50C5 tube was extremely common in All-American 5 and All-American 6 radios, and that's this tube right here. They also used them in some series set record players, so record player amplifiers and things like that as well. So this tube here is in its intended purpose. It's driving an audio transformer, and they're also using this as a modulator to modulate this oscillator coil. So this 50C5 really is not in its intended purpose. It's being used as an oscillator, but it is a vacuum tube and it can be used for multiple different things. So this oscillator coil right here is this oscillator coil right here, that nice looking red coil right there. And what they're doing is they're using the primary of this transformer to act as a modulator. So this is a little bit like reactor or Heising modulation. So the primary of the transformer here is running to the plate of this 50C5, and if you wanted to use this as a transformer to drive a low impedance load, somewhere from 3.2 ohms to 16 ohms, you would use this side of the transformer, and this thing would be acting to transform impedances. Since we don't need to do that, because we're running a relatively high impedance area on this end as well, what we're doing is we're just going to take a tap off of the plate here, and we're going to use this as a modulation reactor, or somewhat like a Heising modulation setup, and we're going to modulate the oscillator coil. So this is going to allow us to put audio into this signal here, and then that's going to be mixed, and it's going to be running out the antenna connection here. The coupling capacitor, to stop you from connecting directly to the DCB plus here, is a 100 microfarad capacitor. Now, microfarad is old speak for picofarad. So nowadays you would just say 100 picofarad. So whenever you see micro, just put pico in there. They also did some pretty goofy things with resistor ratings way back when as well. They've drawn this schematic normally, which is very nice. But a lot of companies, they really made the resistor ratings odd. They really didn't, I guess you could say, put them on the schematic and rate them the way they should have, and I think that was to intentionally create confusion way back when, because there's no other reason for writing them like that. At any rate, so when I come across a schematic with those goofy resistor ratings, I'll definitely point that out. I'll bring that up. And I'm coming across this type of equipment all the time, so we're definitely going to run into those goofy resistor ratings here, probably pretty soon. Here's a 470 picofarad capacitor here. This one here is this capacitor right here. As you can see, it says 470 on it. And that is not an NP0 style capacitor. So it would be a good idea to replace this with an NP0 style capacitor, and then that way it would really stabilize this circuit. The capacitor on this side is just to stop RF from getting into the audio section, so this is acting as an RF block. And of course this is going to also take away a little bit of the audio as well. Anytime you put a capacitor, it's affecting the RF and it's going to also affect the audio. What this is really acting as, though, is it's kind of doing a dual purpose here. It's keeping RF out of the audio circuit, and in the same way, it's going to actually tone down the audio a little bit. You can see over here in the 12AX7 preamplifier circuit, they have a coupling capacitor between the plate of this tube and the grid of this tube. And that's rated at 0.0047 microfarad, or if you'd like, 4,700 picofarad. It doesn't matter whichever way you want to look at that. This capacitor here is also going to limit the audio response of this amplifier. If you were to change this to, say, a 0.01 microfarad, there would be a lot more lows in this amplifier here. So there would be a lot more low frequencies. As you go, say, towards 0.1 microfarad, that would really start to pass the lower frequencies. So you can see they're really trying to trim the audio section in here. And we even have a localized feedback happening within this one little circuit right here. You can see that from the plate back to the grid. Now, a very easy way to remember how vacuum tubes work and how they're wired in many circuits is, if you're an audio guy, signal in the grid, out the plate. Okay, so the signal goes into the grid, and we have amplification, and we have an amplified signal on the plate. The signal on the plate is out of phase with the signal on the grid, and I've explained this in some of my earlier videos regarding vacuum tubes. I won't go through that right now. So So we'll say for a phase inverter circuit where we're using this, say we had a 33K resistor on the plate and a 33K resistor on the cathode, and we had two capacitors running out. The signal on the cathode is in phase, so it's the same as it is coming in, and the signal on the plate is out of phase, so you get your phase inverter circuit. But for normal amplification, signal in the grid, and then it's on the plate here amplified in the grid, and then it's amplified on the plate. We have our coupling capacitor here. So we have two stages of amplification here. It goes through this blocking capacitor and then into our volume control and then into the grid again. And then this is the power tube. This tube drives this transformer so that we can drive a speaker or modulate the oscillator over here. That's how that works. Now, as you can see, there is no isolation from the line at all with this. You can see that, you can plug this cord in either way. So I'll just move this back over here. It isn't a polarized cord, so you can plug it in either way. As you can see, AC or DC. So you can see that this runs here through a 33 ohm resistor, through our selenium rectifier right here, and then we have one filter capacitor. We have another resistor here, which is going to help smooth things for this area over here and also drop voltage just a little bit. And then this goes directly into the circuit. You can see this whole circuit is directly connected to this right here. Now you can see that they've tried to create a little bit of isolation here. You can see the B plus supply here goes through a 47K ohm resistor, and then the ground for this circuit is also, you can see the ground here is also connected through a 47K ohm resistor over to this side right here. So they've tried to give it a bit of isolation, but again, it isn't isolated at all. There is a direct connection to the AC line through here, so that always has to be kept in mind. For my own purposes, if I was ever to put this thing into service all the time, I would have an isolation transformer ahead of this thing to make it safe, because there really is no way to change this design. There's not enough room on this chassis to install a power transformer, right? That's just the way they made things way back when. So we have a filter here, we have a filter here, so you can see the B plus is here, gets filtered, dropping resistor, and helps us with ripple a little bit here. We have another filter right here, and then you can see this section is powered up off of this, and then over here it runs through a 47K ohm resistor here, which is going to also help with ripple, and we're going to also get a drop. And over here we have another filter capacitor right here where this is connected to ground. So any way you look at it, these capacitors here hold a very high voltage charge. You can see 150 volts here, 150 volts. That's the ratings of these capacitors, right? And 144 at this point. So this is going to charge up, and it's going to hold quite a charge. So whenever you're working on something like this, if you ever do work on something like this, you need to make sure that the capacitors are safely discharged before you go into a device like this. So the line cord is unplugged and everything is safely discharged. If there's any problem in this circuit, the actual circuit itself won't drain these capacitors off. So if the capacitors don't get drained, they kind of sit in there like batteries and they hold high voltage for a very long period of time. And then if you go in there and work on something without these things properly discharged, you can receive a really, really bad shock. So these are all things that you need to keep in mind when you're working on something like this. Again, if you don't know what you're doing and you feel uncomfortable with working on stuff like this, definitely do not work on pieces of equipment like this, because there is a direct connection to the AC line. If you're following along, you're doing so at your own risk. Be very, very careful. You can see the filaments of the vacuum tubes here are in series. So we have a 50C5, a 50C5. So we're going to have 100 volts here worth of filament, right? We have a dropping resistor here, and then we have the remaining 12 volts right here, 12.6 volts right here. So this makes up for the residual that's left over, because technically we'd only have 112.6 volts really if these tubes were in series without this resistor, right? So that gives us our little bit of a softener between there. And, if you were running at, say, 110, right? Say if you're running at 110, it's close enough that it would be okay. The current would be there enough to light the tubes. A little bit reduced, and if you're running at 120, then everything would be absolutely fine as well. So they're trying to just make sure everything is safe so that the tubes last a long time, and everything is a-okay with this circuit. So this is one of the resistors that would be very, very important to check if your vacuum tubes were all testing good and then still not lighting up. This resistor would be suspect. Before I attach this to my current limited isolation transformer and variac supply, I want to make sure that there are no gross shorts in this chassis. I want to make sure that all three of these capacitors are good, so there's two in this one and one down here. And I also want to verify this selenium rectifier. So this meter here is very tolerant of testing capacitors in circuit, so I can very quickly and easily read the capacitance. Now this won't test for leakage or anything like that, but it'll at least tell me if the capacitors are trying to do something. Not all meters will do this. Many of these meters will not read capacitors in circuit very well at all. And I'll give you an example of that here in just a moment. This one here is very good for that. Attach that there. 28.7, supposed to be 20. It's reading a little high, but it's there. And 31.5 on the other side. Now here's the trick. There's two capacitors in this can. Both the commons are tied together and run out this side. So if I want to verify that I'm actually seeing these capacitors and there's not other things in this circuit tricking me, I can test these in series. So if I test these in series, since the other one was about 28 point something and this one's 31.5, I should have roughly about 15 microfarad. So we'll test them like this. And look at that, 15.1. So I know I can leave this in here for testing purposes. Again, if I'm about to restore this thing, I would change this capacitor, both these capacitors, this one down here, and I would also change out that selenium rectifier. We just want to see if this thing is going to transmit. So move this out of the way. I'll verify this capacitor on the bottom now. So put this down here like so. And that connects to this point right here. And it's also reading. So far, so good. So now, let's verify this selenium rectifier. Now, the nice thing about this tester here is that it'll test diodes with a really high forward. As you can see here, let's move this over here, and this one over here. As you can see, it'll test microwave diodes, so diodes that are used in microwaves. You can see, test very, very high forward. Very good for testing these selenium diodes. So, selenium rectifier if you'd like. So what I'll do is I will attach this backwards first. And we should see virtually no drop. And I see no drop. This is a good sign. Now, if I see that the other direction, we have problems. So in this direction, I should see a drop. If there's drop there, chances are we're good to go. So here we go, here we go. Bam. Aha, there's the drop. So this is almost too good to be true. I can test this thing without having to change any components at this point. So I haven't tested all the resistors. So far, so good. So we'll leave it at that. There's no shorts or anything like that, and both the capacitors are reading. Oh yeah, I'll show you this other meter here. So here's an example of a very nice meter that does not like to test capacitors in circuit. This is a trap for the new guy. Okay, so here we go. Look at that. Does not like testing this thing in circuit. So I'll test the other one. Same thing. So not all meters are created equal. I really like this meter. It's a great meter. But some capacitors in circuit are kind of, I don't know, tricky. They trick the meters. So this DLM240 is a really good meter for testing caps in circuit. Now, when I originally got this meter years and years and years ago, I purchased this because it'll test modulation reactors up to 200 henries. That's pretty much the sole reason that I bought this thing. And I just found over time that this thing is extremely tolerant at checking caps in circuit. I don't think these things are made anymore. I think these things are out of production now. But they're a really, really good meter. I really like this. And again, that high forward for, you know, the rectifiers and things like that is kind of a bonus as well. So when I purchased it, I just thought, you know, I was going to use it for modulation reactors and broadcast transmitters and things like that. And down the road, I found that, wow, I'm really glad I purchased that thing. It's really a versatile meter. before I go about attaching anything to this thing, I want to see if this thing is going to at least even come to life. So I've unraveled the cord here, taken the little twist tie off. So what I'm going to do is plug this into my current limited isolation transformer and variac supply. Put it down here like so. I'll turn that on. And I'll turn this on. And I hardly see any reaction with the dim bulbs. So I'll just let that sit for a minute. And it doesn't look like the tubes are lighting up. Well, that's not a good sign. See that right there? Look right in the bottom, right here. You'd see the filament starting to glow orange. Nothing's happening. Well, that's not good. All right, I'll shut this off. Unplug this. Turn this thing back off again. So what I want to do now is make sure that the filaments are all okay. I'll just turn this on. And we'll test this tube first. So pins 4 and 5 are the filaments. So if you look at the base of a tube, so you got pin 1, 2, 3, 4, and 5. So I want to see if I've got any resistance between 4 and 5 here. So here we go. And there it is. So the filaments are attached in this tube. This one is good. Let's try this one out. So pins 3 and 4 on this tube are the filaments. So we go 1, 2, and then this is 3 and 4. So that's my fingers touching that. Wow, nothing there. Open filament. So let's try this one here. Make sure my fingers don't touch or I get megohm readings. And that one's okay. 51 ohms. So I've got one bad tube, so I'll go grab another 50C5. That's this one right here. And I'll try again. Okay, brand new tube. RCA 50C5. It would have been really nice if this original night tube was still alive, but it's the bad one. Would have been nice to have at least one original tube in there. Okay, I'll open this up. Brand new RCA 50C5. Okay, plug that in. And plug the cord back into the supply up here. And let's make sure this is off to start. It is. Turn this on, and let's see what happens. Haha, I see the lights. Dim bulbs lit up bright there for just a moment, which is a very good sign. And I already see filament life here. So I'll move this around so you can see that. See the 12X7's lighting up. And so is the brand new tube. And so is that one back there. Everything's lighting up. So that's a good sign. So what I should do right now, while I'm at it, is measure the B+ on the bottom side. If everything's good, I'll put the bottom cover back on, and I'll attach an antenna, and we'll see if this thing is doing what it should. Okay, here we go. Haha. Looking good. Lots of B+ there. Okay, so what I'm going to do now is put the bottom cover back on, and I'll hook up some test equipment around this thing. We'll see if the thing's transmitting, what kind of signal we can get out of this. All right, the moment of truth has arrived. Let's see if the night radio broadcaster comes to life and see if we get a signal out of it. So I'm going to use this radio communications test set to verify that. It's much better than using just a standard receiver because we can look at the performance of the modulation and see what kind of strength level we get on the screen, things like that. So what I'll do is I'll move the focus over to the screen and I'll explain a little bit about the monitor. Let's zoom into that a little bit. So I have this receiving at 1.4 megahertz right now, or 1400 AM if you prefer. We want to keep an eye on the strength level here, and we also want this just to go to a flat line. So when we get a really strong signal with no modulation, this will just go flat. We can listen to it as well. I have the audio turned down right now. So this is off. What I want to do first is give it a small antenna. So I'll just put a small alligator clip on here. I'll just clip that on. So you can see it's a speaker and antenna. See where I've clipped that. Now you might be saying to yourself, well, doesn't this whole system need to be tuned and things like that? No, it doesn't. The oscillator basically just runs out to this antenna through a 100 picofarad capacitor. Now, if this was a ham radio, and say you were in the ham radio bands or something like that, and this had a power amplifier tube, it would need to be tuned correctly into a load. Since this is just coming straight off of the oscillator, any random length of antenna will work that's within the guidelines. So for this device, there are guidelines to the length of the antenna. So that is all within the rules and everything like that. So this is definitely a lot shorter than those guidelines. So even running this thing without an antenna would be absolutely fine. There would be, not a big deal. It wouldn't hurt anything. No parts would get damaged. Nothing like that. So again, keep in mind, if you're going to use one of these things, there is a maximum antenna length that you can use. And again, that's in the rules. So do not exceed that antenna length. Okay, so what I want to do now is turn this little unit on, and I'm going to most likely have to tune this to 1.4 megahertz or 1400 AM. It would be pretty, quite a fluke if it was just right on frequency. So I'll turn that on right now. And of course, that's providing this thing is even going to put out a signal. Let's find out. So I'll turn this up. Have to let all the tubes warm up. These are coming into emission pretty quick by the looks of it. And what I need to do is tune this little frequency adjustment right here until I get maximum signal here, and I want to see nothing there. So I'll put this on here right now. And see if I can find it. I don't know where this trimmer is sitting. Go this way. Let's move this out of the way so you can see the screen. Oh, it's getting quiet. I hear attenuation relays clicking. That's quite the signal. 3 millivolts of signal, so it's really close to the receive antenna. So as you can see, the scope has gone flat, and it's receiving. So this is transmitting right now. Now, the length of the antenna and the actual antenna itself will load this circuit, because technically this is just an oscillator. So if I remove this right now, chances are this will go off frequency. Let's find out. Yeah, see that? It went off frequency. So with no antenna, I'll just put this back in here again. See how I had to retune that? With no antenna and this thing sitting right here, I basically have 1 millivolt worth of signal with just this terminal open right next to this antenna. You got to keep in mind that this thing is receiving, and it's what, 3/4 of a foot away, something like that. So we can probably even test this without that antenna. Would be absolutely fine. So what I'll do now is I'll give this some audio. So I'll back this out a little bit so you can see what's going on. So the signal generator here is set to 2 kilohertz with an output level of about 20 millivolts. That should be fine to drive the audio. So this is going to put out audio as well. So I can drive the audio into this little unit here. So I'll put this, it says AF generator output. So that's audio frequency generator output. And I have my little RCA cheater plug right here, so just plug that in like so, and clip the test terminals on here. Like that. So now that I've done this, I might need to retune this again. Let's just make sure, because I've connected wires to this. Right about there, that's good. Okay, so I'll give this a bit of... Wow, look at that. Let's turn that down. That's actually looking really nice. Look at that signal. At about 66% modulation. Wow. So I'll just zoom on into that. I'll turn this down and zoom on into that. So right now I'm adjusting the volume control, or the gain control you could call it, on the front. Look at that. Modulates right up to the top. If I turn it right up, that's it. It tops right out right there. It's working extremely well. And that looks really nice too. Look at that. Modulation is looking really good for such a small device. Looking very, very nice. So what I'll do now is I'll attach this antenna back up to this again and retune this. That's at 3 millivolts. That's a big signal. I can hear the attenuation relays clicking in this. That was an attenuation relay clicking there. Yeah, it's looking good. Antenna or no antenna, it looks really, really good. Wow. I'm very impressed with this little night radio broadcaster. So any of you that are going to rebuild something like this, this is the kind of results that you should get. I don't honestly know if it would get much better than that. So putting new capacitors inside this thing and, you know, swapping out that selenium rectifier could only make it better. You know, have more filtering and, you know, or better filtering and a better diode in there and everything like that. So all in all, this thing is working great. Absolutely great. So zoom back out here. And put this back down to the broadcaster. Yeah, it's working very, very well. So just get this out of the way. Very impressed. Basically nothing done to it. Just a bad tube, really, is all this thing had, and the way it went. Makes me wonder if the reason this thing was put back into the box or sold off is because one of the tubes went away and somebody just didn't fix it. Very, very interesting. In the last video's trivia question, I asked, what is this device right here? And if you're just tuning in now and you want to guess what this little thing is, pause the video now because I'm about to give the answer. This is a gas-filled phototube. So this is an S1 response, so this is designed for light-operated relay applications. Now they use tubes like this in all sorts of different applications. They use these in film projectors, early film projectors, and they use these things in smokestacks or in chimneys way back when. I have a pretty interesting story about that. There are different variations of this tube, not this particular tube, but variations of it. And they even used little tubes like this in headlight dimming controls in some of the early cars. So the number of this tube is a 921. So those of you that guessed 921 and phototube got it right. So now for today's trivia question. This will be answered in the next video. What is this thing? I'm not telling you any more about it. You guys can guess what this is. answer in the next video. Thanks for stopping by the lab today. I hope you enjoyed this video involving the AM broadcaster. Really is a neat little device. If you did enjoy the video, you can let me know by giving me a big thumbs up and hang around. There'll be many more videos like this in the very near future. We'll be taking a look at vacuum tube and solid state electronics alike. So there will be a lot of repairs, restoration, troubleshooting procedures, and even some circuitry design on this channel. So if you haven't subscribed, now would be a good time to do that as well. If you're interested in taking your electronics knowledge to the next level and learning electronics in a very different and effective way, you're going to want to check out my ongoing electronics course. And it's much more than an electronics course as well. I'm sharing many of my electronic designs and inventions up there as well. What I'll do is I'll put the link to that under the video description. So just below the video is a description, and just below that is a show more written in capitals. If you click on that show more tab, it'll expose the link. Click on the link and it'll take you right there. I may even pin the link at the top of the comments section as well. So until next time, take care. Bye for now.